Koen Bertels for this podcast. This is a kind of a podcast which I was always waiting for. I've never idolized anybody in the quantum world because I'm just an enthusiast who just make notes like this, and my home is filled with books. But I've never worked on the quantum field in a very extensive fashion because I'm an IT guy who just wants to explore something new. But trust me, when I saw Cohen, sir, it's an amazing view on what he has about quantum computing because quantum computing is been misunderstood or has been hyped, or is it said as a hope? We still don't know. We are yet to demystify a lot, and we are yet to say what are the actual potentials of quantum computing today. Thus, I have the best guest for you, Koen Bertels, for this podcast, who is trying to demystify all your doubts regarding the quantum computing and what are its right potentials. So yes, I think Koen Bertels, sir, you can share your screen. This is my
Yeah,
first attempt in having a slideshow in my podcast. I think it's going to turn out good.
yeah. Wait, then just a second. I try now again to share my screen, and
Yes, share your screen, sir.
I will try to make things a little bit, hopefully more realistic. Yeah, that is, I
Sure,
think,
sir.
the biggest
So
concern.
before just moving
Yes.
forward to the slides, you can share your screen. But I want to ask you this some of the philosophical questions, like two questions that I really wanted to ask for you, so that you can really talk on it in a in your own way. I just want to ask, like, how far is in human understanding just having the capability of demystifying what is quantum world, or else I just want to simply ask you on a scale of 1 to 100, or else on a scale of 1 to 10, what is our understanding about the quantum world or the quantum computing?
Wait, and 100 is the maximum.
1 to 10.
1 to 10. And so so 10 would be like perfect, and we understand everything, and then
Yes.
one is we're basically nowhere. Okay, I will now make a very disappointing statement. We're maybe at 3 or 4. Yeah, but I will try to explain that. Yeah, and so do you still hear me? Yeah, you still hear me, right? So this we're basically we I do believe quantum is the most dramatic change that I've seen in my professional scientific life. And I did a lot on FPGAs. I did a lot on accelerator kind of technologies. I'm a computer engineer. I'm not a computer scientist, but I'm not an electrical engineer, but not a computer scientist. I'm a computer engineer. So I'm used to making computers. Yeah, and so that's what I basically did already for 8, 9 years now in quantum. So I have to say we're only at level 3. And I do hope that maybe in 5 to 10 to 15 years, sure, this is going to happen in your lives. Yeah. Maybe in mine too. I do hope that I get a little bit older than what I am now. Yeah. But it takes another 10 to 15 years. Nobody's talking about that. Yeah. And this is my main message that I do. I want to make it clear why I'm saying that. And it's not because of pessimistic. I'm a pragmatic, realistic kind of scientist, and that is my core of what of my messages that I will do today.
Yeah, I just had one more question, like, how far is our colloquial computer, our present day modern age servers, our computer, capable enough to drive such a quantum node or the quantum bit? No, I know it's all complex. So, how far is this chemistry of our modern age computing and the quantum computing really working out for the world? Do we need something as a breakthrough that is really required for this quantum computing?
Well, now I'm already giving you the explanation that I tried to bring today. Yeah, but what I think is essential to understand is that quantum algorithms, on whatever topic they might be developed, you can execute it on a classical machine, a classical computer. You need a lot of memory. Yeah, I will explain that too. Yeah, so we do need maybe supercomputers. Yeah, but we have maybe too many supercomputers. Yeah, and everybody phone. Yeah, an intelligent phone, and we take pictures with that, whatever it is about your mother, your girlfriend, or your boyfriend, or whatever it is. Yeah, and where are we going to store that information? We don't even know. We are saturating all of the technology that we currently have. So there are many radical changes that we need. We all know about global warming and things like that. I will not go into those kinds of topics, but this is all very closely related. So what is it that we need? We need substantial breakthroughs in the physics part. I'm not a physics person, but in the physics part. But we also need substantial breakthroughs in algorithms, in programming languages, in microarchitecture, in whatever I'll be talking about today.
Sure, sir. Sure. I think it's going to be amazing.
I'm connected to two universities these days, which is the University of Porto, which is Portugal, south of Europe, and Leuven, which is Belgium, because I'm Belgian by nationality. Yeah, I do have one Indian PhD student, Aritra Sarkar, and he's doing his PhD on quantum genetics, which I already worked on in the past, but now he makes a quantum version of those algorithms. And it is amazing to see how good he is. Yeah, that's not just to give a compliment to India, because you know Indians or intelligence is everywhere. It's not only in Europe, it's not only in the United States or India or whatever. No, all countries have intelligent people. Yeah, and my goal is to really unite them together. I also had a Pakistani guy. Yeah, Pakistan, India. You know. Yeah, Mahatma Gandhi. I will not talk about him either. Yeah, but Pakistan. So Imran Ashraf, he's now an assistant professor in Pakistan, and he stays very intimately connected with the quantum research that we're doing. And you see here also, where's my mouse now again? Here, you see here in the top left side there is QB. Yeah, so this is a company that I oh yeah, okay, that's okay, that's a bit okay. The animations are not so good, but that's how my computer works these days. But Cube is a company that I'm in the process of making. Yeah, and just that you guys know, I will not name people's names. Yeah, but I have a Malaysian investor. So just an indication, the world is dramatically changing or drastically changing towards Asia. So India should be happy because China is a dominating factor in this entire, well, in quantum too, but also in the economic world and political world. That is China, and so it is clearly moving towards that region. Yeah, and so Aritra and Imran, they're co-founder with me of QB, together with the Malaysian company that he has. Yeah, so that is what I'm currently working on. And what is it that we want to make here is an accelerator. Yeah, I will not call it a computer anymore. Yeah, because I've never read a good book about the quantum computers. Yeah, but I work myself on accelerators, and so that is why I call it now quantum accelerators. I do think I know what that actually means. Yeah, and it is clearly going that we want to go beyond the NISC kind of idea. That was in 2000, you know, straight. Okay, the drawing is very bad, but okay, that's what it is. Yeah, so that was by John Preskill in 2018. He's a physics person, and he gave a talk about because we always looked in one particular way of making a particular kind of quantum bits, which we call qubits. Yeah, and he said, like, don't do surface code anymore. Don't worry about that. I will not explain all these things because I only have, let's say, 45 minutes to an hour. Yeah.
You can take your time. You can take your time. I have done podcasts for 1.5 hours, 2.5 hours. Recently, I did a podcast for 3.25 hours. So you can take your time, sir. No worries.
Yeah,
I think John Presto is the guy who framed the work quantum supremacy, if I'm not wrong.
Yeah, but he basically said, let's stop doing the surface code because we're wasting qubits to be ancilla helper qubits. Yeah, and we should rather be focusing really on the physical aspects to make them better. Yeah, and I will explain that a little bit in what I'm talking about. So if there are computer engineers or EE people listening to this video at some point, yeah, I wanna mention transistors. Now we have phones, we have computers, we have supercomputers, we have cars which are filled with processors. They're all based on transistors. Now, from Lilienfeld, who in 1934, defined the first time what is a transistor. Yeah, that's this person here. And then there was a lab in Bell Labs in the United States, and it still took like 14, 15 years before they implemented in an operational way one transistor, one, yeah. And then it still took like 40 years before we reached in 1970, yeah, the VLSI level, a very large scale integration VLSI. Yeah, that's what you need to understand. So it's only at that moment that we were capable of producing in larger number these transistors. And it was only in the 1980s, so about 10 years later, that IBM, yeah, which I do hope you know, yeah, started making personal computers, and which was the start of a growth of computational performance that was given to anybody in the world. Yeah, so that is so it took 30, 40, 50 years before from an idea to a VLSI implementation. Yeah, now in quantum, I will talk about that later, we're in the pre-transistor phase. The physics people, they're still fighting among themselves how to make quantum bits called qubits. Yeah, I will not say quantum bits anymore, I will call them qubits now. Yeah, because it goes from diamonds to Majoranas. Yeah, I will say something about Majoranas later. Yeah, to semiconducting, superconducting, ion traps, graphene, anything can be used apparently to make qubits. Where are we? Nowhere. Yeah, that's a big insultation, but I say it in a constructive way. Yeah, this is simply where we are. We haven't decided yet how to make a good quantum bit. You know, and I will give numbers about that later on. Yeah. Why do I still believe in quantum computing? Yeah, is of the computational power. Yeah, and this is a figure you can easily find on the internet. If you Google the power of quantum computers, you will see this kind of thing. This is a little bit modified by me. Yeah, I added one word, and this is something that I will repeat multiple times. Yeah, perfect qubits. This immediately means for whomever will be listening to your podcast, to this interview, and to this talk, there is one main message. There is no reason whatsoever to go into the quantum physics, to go into whatever the physics people are capable of offering. Don't do that. You're making things impossible to solve, yeah, because they have to solve their physics problem, and we have to solve many other problems, and that is the main thing. But the computational power, so you can combine these qubits, yeah. And every qubit has two base states, yeah. So if I combine two qubits, I have 4 base states, looking like this. I can combine 3 qubits, I have something like this, 8 fingers, so 8 states. And I can keep on going, yeah. 2 to the power 10 is 1024 states. I can even go to 300 states here, and this is a number I don't even know how to pronounce it, yeah. But this is a number which is estimated to be bigger than the number of atoms in our known universe. And we are more than 10 planets. We have maybe 15, maybe 20. I don't know anymore what the number is, because we keep on discovering new planets, yeah, small and big, yeah. So this is an incredibly big number, but that simply shows that if we could process data in a parallel way, yeah, parallel way in the quantum, this gives us computational power we cannot even imagine, yeah. And this is very important that I emphasize that, yeah. Now, what is also important is the dark box here below, yeah. If we add one more qubit, yeah. So if I have 2 qubits, now 1 qubit has 2 states, 2 qubits is 2 to the power 2, 4 states, 3 qubits is 2 to the power 3, 8 states, and it's always 2 to the power, as I wrote right down here, yeah. This is the expression, yeah. So if I want to add one more qubit, it's 2 to the power 301. It simply doubles what we have. 2 to the power 300 is already the big number that we see on the screen. We simply double the amount of data that we can process. It's like, excuse me, this is incredible, yeah. Now, unfortunately, the world is not so simple. We all know that, right? So we have to do a lot of things, yeah. And that's why I say we're not there yet. Yeah, whatever people will say is always it can be orthogonal to what I'm saying, and maybe I'm completely wrong. And I will say that in 5 years, if I'm completely wrong, I will say I was completely wrong. Yeah. But if I'm right, I will keep on saying, I said, look, guys, I already predicted this, and I predicted this already many years ago. Okay. But so what is my personal background in quantum? Yeah,
Yeah.
which is
Coen,
already
sir, I
quite
just
well.
wanted to ask you
Yes.
this one question. Are we very
Yeah.
close to Avogadro's number?
Sorry, what?
Are we very close to Avogadro's number, at least in terms of computation?
A big what number?
Avogadro's number, 6.022 into 10 power of 23. Avogadro's number, the number of molecules in the molecular weight of an atom.
Ah,
Avogadro's number.
yeah, I don't even, I'm not fully understanding what you're saying. So I don't know, even know how to answer that, but
Yeah, fine. I think I asked about Avogadro's number, which is 6.022 into 10 power of 23. Are we very close to that amount of computation, at least in future, at
well,
least?
well, again, I have to make sure that I say, okay, wait a minute. Yeah. Classical computing and quantum computing are really orthogonal. Yeah. Quantum computing is an in-memory computation. So I have qubit states on which I will apply directly on the qubit quantum gates. In a classical machine, I have a processor, I have memory, and I transport the data to the processor. I do something and I transport the information back. This is not how it's being done in quantum. Yeah. So
Yeah.
where are we? Yeah. Let me explain.
Continue,
Let
sir.
me continue
Continue, sir.
explain, because otherwise I get confused myself. Yeah.
Sure.
Yeah. So I just want to say that I worked for Intel. Yeah. They came to my university. Well, when I was in Delft, University of Technology. Yeah. That was Intel that wanted to update its roadmap, and they went to Stanford, Princeton, Harvard, MIT. Yeah. And at some point, they also came to Delft, and then they told me, say, hey, Bertels, say something to Intel about what you're going to be doing. Yeah. Now, just know one thing, a little anecdote. Yeah. 1 month before they told me that I need to say something to Intel, the physics people in Delft, they asked me, what is it that you're going to be doing now? I said, I don't know. So I did a lot on FPGAs, which is also multi-layer, yeah, as an accelerator to a classical processor. And I simply replaced the word FPGA by quantum. And I was completely destroyed by the physics people. They said, what a bullshit story. Go back to your office and think again. I said, yeah. And then they said, like, now you need to talk to Intel. I said, okay. In the end, I said, like, I only have one story. And I brought the same full stack layer, yeah, on quantum. And Intel reacted in an incredible way. He said, this is the only place on earth where we hear how to make a quantum computer. We're going to finance all the research in Delft. I said, oh. And from then on, they did not dare to attack me anymore, yeah, which they still did afterwards. But okay, that's what it is, yeah. But then I was suddenly like, okay, he seems to know something, yeah. But again, so I'm doing now. I continue working the way that we did, but whatever we did, let's say for the quantum physics, I've done it, yeah. I know how to do it, and we can go to maybe 150, 200 qubits, yeah, physical qubits, and we'll see. Okay, whatever it is. Now, just here. Yeah, I want to highlight this phrase. Yeah, the Majoranas are out. Yeah, because that was a colleague in Delft. Yeah, who claimed that he discovered this very hidden theoretical particle, which called Majorana, which is by an Italian who made the formulation. There is something that we need, and the Delft professor, he claims he discovered it, and then he sold his group to Microsoft. Paid a lot of money for that to him. He stayed professor, got rich. Now has to admit, I'm not even capable of making a single qubit with these Majoranas. He had to withdraw his Nature paper. You see, so that simply means like what I'm saying is true. Yeah, is the first proof of my statement that we're not there, and the physics people, they still need to fight out. Yeah, fight out among themselves how to make these qubits. Okay, so this is what I wanted to say on this particular slide. So we still have challenges. We're not there. I still believe extremely in the use and in the possibilities of quantum. Yeah, but we need to start going much more into this perfect qubit kind of thing. Yeah. Now, if you know IBM, you know that IBM has created also a platform called Qiskit, yeah, and that's it's a free platform. IBM is super focused on superconducting qubits, not semiconducting. Intel is more in the semiconducting now, and IBM is still on the superconducting. But they make the software free, and actually they have a compiler also, which has the option to compile for perfect qubits. I discovered that like 2-3 months ago only. Yeah, so this is again a clear indication that I can invite anybody in the world, whatever your discipline is, to enter into the quantum world and start thinking about it and start developing, yeah, your own algorithms. There are many languages. Yeah, IBM has one. QB also has one. Yeah, but I will talk about that later. What is the main challenge is that the qubits, and this is a graphical, a visual representation of a single qubit state, yeah, which has 2 base states, yeah, even though there are 3 dimensions in which you can have it, but you see you have the 0 state and the 1 state, yeah, and here the 0 state and the 1 state, but it can also be the plus and the minus state, yeah. So the plus and this is actually a plus state, and this is a minus state, and this is a 0 state. This is Z state, yeah. So, but you see here a qubit psi, yeah, this red line, and all of it, and this is true for all of the quantum technologies that we're working on. They always go to the ground state. That basically means something like this, yeah. So you see now it goes to this particular ground state. So at that moment, you lost all of the information that you've already achieved, all of them, yeah, yeah. And so that is for me a big problem. Let the physics handle people that do that. Yeah, I cannot solve all of the problems. I'm very honest. Yeah, I can work on what I understand, but I cannot do everything. Yeah, so this is clearly what the physics people need to solve, whether they're in semi, super, graphene, ion traps, whatever it is. Yeah, Majoranas are out. Yeah, so that needs to be clarified. Yeah, and so this is important. Another well, no, I will, otherwise I get to so the errors that we have. Yeah, that's this particular graph. You see here. Yeah, this is what we know in CMOS. Yeah, CMOS is what we make classical computers of. Yeah, and we make trillions of transistors per year. Yeah, yeah. But this is where the physics people are in red here. And so you see it's 10 to the minus 15, 10 to the minus 16. That's what I show here in this table. And the physics people, they're 10 to the minus 2, minus 3. So you see, this is a billion. Yeah, 10 to the minus, this is 10 is the base state. Yeah, so 10 to the power 9 is about a billion. And so they're making 100 errors up to 1,000 errors with each run. Yeah, so this is incredibly big. Yeah, and these are the errors that we can tolerate, that we can handle in any classical technology, classical, not quantum technology. So so if you know that this is a billion, yeah, this is much bigger than a billion. Yeah, so this is simply the big challenge, yeah, that the people have to understand, that we are not there yet at all. Yeah, I want to be very clear on that. One company that you may know is Gartner, which is an IT consulting company of the United States. And they've been looking at many different kinds of technologies worldwide. Yeah, what people are interested in. And they came up with what they call the hype cycle, which is the thing here. The hype cycle, which is what is the graph that you see here. So everybody's super enthusiastic in this first phase, yeah, until they see like, oh, it's not really delivering anything that we were promised. Yeah, then everybody will move out. Yeah, yeah. But of course, if you keep on believing, then there is a future. Yeah, and you can find maybe the hype cycle curves of Gartner maybe like 5, 6, 7 years ago. And then quantum computing was maybe somewhere much lower, and you do see it is increasing in importance. Yeah, so that is why universities, yeah, and that's my main point. They should say, okay, look, we're going to be looking at where we are right now, but this is the target point that we want to achieve. Yeah, so let's not ride the hype cycle. Yeah, what companies do. Yeah, but not. I do hope universities should not do that. And that is also a message that you should bring in India, in Pakistan, in China, that I bring that everywhere now. Yeah, this is an open call to any university, that says, okay, we want to understand what the impact is of quantum on our field. Yeah, and trust me, you need to do a PhD in quantum. You need to have set a team in quantum expertise, and then you need to work on, you need to analyze the big problems and work together on making some kind of accelerator. Yeah, and this is exactly what QB is aiming to do. We're not a university, but I do hope that will change at some point. Yeah, but this is an important curve to look at. This is a graph I made myself. Yeah, to show where we are in the scientific field. Yeah, so I made that already maybe 2 years ago. Yeah, so it's not 2021. Yeah, but so this is where I was very much interested or working on in the first 5-6 years in Delft. Yeah, but of course we haven't solved anything. Yeah, and you know the difference, the different error rates are so big that it takes a long time before we reach a good integration technology. Yeah, maybe in 10 years. Yeah, that's just a guess. Yeah. So that's why I now move actually to this part. Yeah, and this is an open invitation again for anybody who is interested, whether you do medicine, whether you're in economics, whether you're in biology. Yeah, all of these things will be impacted by quantum technology. Yeah, and you better want to be ready in the teaching and in the research by the time that we hit the market, because it will hit the market. This is where we can start integrating again the technologies with the applications, yeah, the hardware with the software. So this I think is important to understand. And you see, I already start talking to entrepreneurs. I talk to computer science people. I'm a computer engineer, as you see here. Of course, you work with mathematics. If you're not good in mathematics, stay away from quantum. Yeah, stay away from quantum. Yeah, because it's a specific kind of mathematics. It's tensor mathematics. Yeah, which was developed actually maybe 50 years before quantum mechanics as a field was defined. Yeah, so you see, but it's a very dynamic field. It's very nice to work in something in which many fields can interact, and everybody has its particular part to contribute. Yeah, so this is where we are. This is where we were in the first several years, and where the physics people will keep on working. Yeah. And this is what now my open invitation is. Yeah, and you see only 10%. That's my guess. Yeah, because it's too big to count. Yeah, but it's my personal guess. Only 10% of quantum computing research is done. Yeah, and in this upper rectangle. Yeah, so this is again an open invitation for that and try to be. The big advocate for this vision. Okay, in whenever you give a talk, yeah, or make sure that this is well understood by people. Yeah, so I already showed. Oh, okay, it's a repetition of slides apparently. Okay, that's what it is. Yeah, so how are we going to build such a quantum accelerator? Yeah, I'll make it a little bit more pragmatic. And yes, of course we need good qubits, but we don't have them. So that's why we go for perfect qubits. Yeah, and I will explain that in actually now on this slide. Yeah, so you always have a number of qubits n, yeah, which is a variable, and you have a base state in each qubit. So that means in the end you have 2 to the n amplitudes, because the amplitudes, yeah, I have not shown that basically. Yeah, but I will show that in the next slide. Yeah, in the next extension. Yeah, so if we can go, if we work on perfect qubits for whatever application, yeah, we can maybe go to 100 and 150 perfect qubits. Yeah, that means there is no decoherence, no errors in the quantum gates. So the decoherence, yeah, going to this ground state, as I showed before, yeah, and operations is you need to, these are analog phenomena, and these are angles that you need to shoot, yeah, or you need to rotate the vector. Yeah, your qubit vector in a way, and it's overshooting or undershooting. Yeah, so in perfect qubit, no, we do correct rotations. Yeah, that does not mean it will happen in physics. Yeah, but okay, let them also solve their problems. Yeah, so where do you have the amplitudes? We have here the alpha, Yeah, and we have the beta here. Yeah, but this is of course the alpha, this is the beta. Yeah, that represents the amplitudes of the 0 and the 1 state. Now the amplitudes, yeah, which I mentioned here on the top of the screen, yeah, the amplitudes, they're actually consisting of two real numbers, yeah, and the imaginary number. Yeah, so this is a complex number. Yeah, always. Yeah, so whether you like it or not, that's the way it is. Yeah, yeah, because this is something that we can never visualize. Yeah, so the alpha has a particular a and b, a and b real numbers, and the imaginary number, and c and d for the beta, and the imaginary number is the square root of the -1, right? I think we understand that. Yeah, so that means if I have 2 qubits, if I have 1 qubit, I have 4 amplitudes. Yeah, so that means I have 1 amplitude here and 1 there. So that means 1, 2, 3, 4, yeah, are the real numbers that I have in the amplitudes. It's 2 times 2 to the power 1. Yeah, so 2 to the power 1 means, yeah, I only have like 1 qubit, but I have 2 base states. Yeah, and so it depends then how many bytes you use to represent the real numbers. Yeah, maybe it's 4 bytes or 32 bits, or it's 8 bytes, 64 bits, yeah, for double precision. And that immediately say, if we're going to execute that on a classical computer, and it's 2 to the power n, and n is maybe going to 50, 2 to the power 50 is an extremely big number, because you need to double that amount to represent the amplitudes of those 50 qubits. Yeah, because they're in superposition, so that immediately explodes in the use of the memory. Yeah, so that's why I highlight this is like a summary. Yeah, this is what we compute. So 2 to the power n qubits, 2 amplitudes per qubit. So that is why this is the amount of memory that we need, yeah, to represent these n qubits, yeah, in superposition. Yeah, so just let us not forget that. Yeah. Now let's go back to let's say making an accelerator. That means we need to make the full stack. It's not only just the number of physical qubits that we can make. Yeah, it's how they interact with each other. What kind of operations can they do? What kind of applications do we develop with that? Yeah. So that's why I say also it's a fully integrated, yeah, executable, yeah, number of layers of this quantum accelerator. And of course, if we have a classical machine, I will now in my research, yeah, and I'm working with Aritra, Indian guy, yeah, on quantum genetics. We don't use any physics, quantum physics, yeah. We use our own simulator that we developed ourselves, yeah, which is, I think, pretty good, pretty powerful. But of course, it needs to run on very, very strong computers, yeah. So it's expressed in these perfect qubits, yeah, and we need also to express all of these amplitudes, so that is where the memory consumption comes from. Yeah, this is just a figure, yeah, of how we started so many years ago, yeah, with a Chinese student and a Greek guy, yeah, and then a Chinese lady, she joined too later in the team, yeah, and then we grew to, let's say, 12, 13, 14 people, yeah, and this is now my current vision of the full stack. This said, I will send you maybe afterwards, after this presentation, I will send you what we call the big paper. Yeah, I put a lot of effort with Aritra and Imran. Yeah, they were the main authors, so we were the main authors, and I included a couple of other people on what we understand now to be a quantum accelerator. Yeah, and I talk about the physics and everything and the concepts, and but that's like 39 pages long. Yeah. But I will make that available. It's in the public domain, yeah. So you Google it, yeah, or they can mail you, and then you can distribute it too, yeah. So this is basically the full stack. Now, just as a little anecdote, 2 years or 3 years ago, I was at the DATE conference, which is one of those conferences in Europe, yeah, Design, Automation, and Test in Europe, DATE. Yeah, and we brought a paper there, and that was back then the full stack. And I was invited by an IBM quantum person for dinner, because I had to give a talk the next day at the session that IBM organized on quantum computing. I said, what do you do in terms of full stack? and microarchitecture. He said, no, we don't do that. It's too early. Yeah. Now we're 1 year later, 2019. Yeah, you find here that they published the paper, and yes, they suddenly start doing also the full stack. This one, similar, of course, not the one that we have, but it's good. The basic idea seems to be grounding. Yeah, I already told you about where are we now in the quantum world, and you see here the Majorana is simply blocked. Majoranas are out. Trust me, they stay out. Yeah, yeah. And where are we now? So this is and I just highlight this. I put this slide in because at some point I went to the, there's a quantum flagship, which is a big European project, yeah, for quantum computing, yeah, only consumed by quantum physics people, yeah. But I went to the EU responsible for that and said, look, yeah, I have a bit of a problem because you need to submit project. I submitted 4 projects, result is 0, yeah. Yeah, I said that because the physics people are nowhere. And he himself, and I will not mention his name now, he said, you know what, the physics people, if they're honest, they cannot even make physical qubits at 10 to the minus 2. I said, well, I'm very glad that you say it, because if I say that, they would kill me on the spot. Yeah. So I don't know now what the effect will be, but this is simply to show that this is a perception. I'm not the only one to have that perception. Yeah. So many people in leading situations, they see that. Here I see, again, I show our full stack. Everything in red means it is available. Yeah, that is what I show here. Green, we still need a lot of people. It's an open invitation. If you're interested in testing quantum software, yeah, simply do it. Well, do contact me. Yeah, because a lot of the things that we did for the Intel. Yeah, and then that basically means it's in the public domain. Yeah. Whether you will find a good version right now, that I don't know. Yeah, but I'm willing to share that with a lot of organizations. Yeah, you see here that we have our own simulator, which is called QBSim. Yeah, and so that means we work with perfect qubits and implement and execute. Yeah, so that is what we are willing to do for companies if they pay QB. I have to pay Aritra and Imran too, and other PhD students, right? So that is very clear. Yeah, but that is basically the core of what we're doing. So this is another way of viewing. Yeah, so what QB is going to do, and I do hope that other universities, yeah, and other countries will also start doing that. Yeah, we only work on this part. Yeah, so this is yeah. So we will work on our simulator, yeah, and work on application. And of course, we did that for Intel. Yeah, Intel at some point both had semi and superconducting qubits, and it was simply a compiler issue, complicated compiler issue. That is also true, but compiler-wise, we can translate, yeah, our C-quasm, which you see here, yeah, in an E-quasm. Yeah, and the E stands for executable quantum assembly. Yeah, and then it depends on what kind of the quantum technology it is that you're looking for. But yeah, we did already super and semi. Why not ion traps? Why not graphene? Yeah, that depends on who will win. Yeah, and nobody's winning right now. Okay, but companies like IBM, yeah, Alibaba in China have a lot of money, and they put all their effort on superconducting. That may be the reason why that technology will win. Maybe Intel will win in semiconducting. That's still, but again, I don't know. I cannot say anything about it. But this is what we are. So I think the green part, yeah. So what you see here, yeah, that is where I think still a lot needs to be done. Yeah, and again, open invitation. Yeah, if you're interested. Yeah. So this is what we have. Yeah, but we need much more, and you see the list is much even longer. Yeah, yeah, because everything needs to be optimized, yeah, and improved and whatever it is. Yeah, but there are many things that we need to do, and I will talk about those aspects yeah, in the next slides. Yeah, because we are going to run everything on a supercomputer. Yeah, the QBSim, written by actually another Indian guy, Ravi, yeah, who will also start doing his PhD with me in a couple of months. Yeah, so he made a much better version of the simulator that we had before. Yeah, he has some super smart kind of insights. Yeah, such that we can easily run it on very large and very powerful supercomputers. Yeah. So this is a bit kind of an idea. Yeah, I'm not saying that we're there yet, because we still need to connect. We're doing that process right now with one supercomputer, but in principle, we could combine multiple supercomputers. Yeah, so such that we can go to maybe 100, 150, 200 kind of qubits. Yeah, because we need a lot of memory for that. Yeah, that is something that we still need. Yeah. Now, what are supercomputers? Yeah, I just list here the 10 fastest supercomputers in the world. Yeah, there are several hundreds of these things. I think you see Switzerland here. I think Switzerland as a country, it's a very rich country, true, has about 20 supercomputers in a small country. Yeah, but there are enough supercomputers, but you see China is already very powerful in these things. Yeah, and China is making its own processors. Before, up to 2 years ago, they always bought Intel processors. Now they make their own processors. They don't need the United States anymore. Yeah, you see, the shift is absolutely happening. Yeah, this is a clear indication of that thing. This is the Taihu Lite, yeah, the supercomputer in China. Yeah, I don't know whether you, I don't read Chinese. Yeah, but that's what it says. Yeah. These are the memories that you can have on supercomputers. Yeah, and I think we need to go up to, let's say, zettabyte, which is 1000 to the power 7. Yeah, so just to know that 8 bits is 1 byte, then 2 to the power 10 is 1024, which 1 kilobyte. Yeah, and so that gives around 1 million kilobytes. Yeah, is what you have here. Yeah. And so you still need this is substantial pieces of memory that we need, classical memory. Yeah. Now, just because I did not say that, in the quantum physical world, the parallelization is actually done in an implicit way. There is not a single physics person who knows about parallelization. He simply knows that his device is doing it in parallel. Yeah. Nobody understands why. Nobody, if I say nobody, not a single person on earth knows why that is. But that's what we do see. Yeah. So just that is important to realize. Yeah. This is another visualization of the memories. Yeah. And now I reduce the numbers to it is still as big. Yeah, but it's a bigger graph. You see here to the power 10, and this is the power 2. And we go each time to about 98 qubits that we're combining. Yeah. And of course, even in the quantum physical world, yeah, and 2 to the power, we still need a lot of memory, but it's only once we go to really, let's say, to classical bits and bytes, we need much more memory. Yeah, this is just an indication of the challenges that you need to have in order to go in that direction. Yeah. So what is the main focus? We worked a lot in the first years on fault tolerant quantum computing, yeah, FTQC, fault tolerant, yeah, implementation. So whatever semi-superconducting qubit we have, yeah, and now it is more moving in let's say in simulation. But actually, since Neskill paper, this is now going to NISQ, yeah. So that means we need to make we need to combine multiple physical qubits to make one logical qubit. Yeah. And he said surface code needs 49 physical qubits to make one logical qubit. So I said, drop it. Yeah. Go back, let's say 20 years ago, when we had smaller scale logical qubits with much higher, which even worse error rates. Yeah, but at least we can do more testing and more experimentation at the physics level. That's what Prescott basically said. Yeah. We do again something completely different. Yeah, we go now. Yeah, in this blue rectangle here. Yeah, and we go to functional simulation. Yeah, with perfect qubits on classical computers. So we stay away from the fault tolerance. Yeah, because we eliminate all of the problems that we have in perfect qubits. Yeah, so that's why we can simply look at the functionality of quantum algorithms. And I think this is very good to bring as a message to the world, to everybody who is interested in going to quantum, do it in that particular way. Yeah. And that's why the big paper that I'm willing to share, yeah, you should read it. Yeah. And then people can always contact me to have an operational translation of what they want to be doing, yeah, I can help people with that. Yeah? So this is basically, again, what is available with all the yellow stars. Yeah, this is using our QB sim. Yeah, in QB sim, yeah, there is a free version, but we already improved QB sim. Yeah, thanks to an Indian student. Yeah, so this is a proprietary now by QB. Yeah, and Ravi will also do his PhD in a QB context, but in a university, of course. Yeah. So that is and that will most likely be a combination of these two universities. Yeah, that is what the goal is. Yeah, so this is basically what QB is going to do for companies, organizations. Yeah, because this is available. The microarchitecture, we're currently making a generic version of the microarchitecture, and I will show what that means. Yeah, the language is there, and the applications we are asking companies to give us applications. Yeah. So what we currently are doing is, as I said, with Aritra is on genomics, and Duarte is a Portuguese student, and he works in quantum finance. Yeah, I will not go into that, but again, the list can be incredibly long. Every field, yeah, that needs computation, they have to ask themselves the question: what is the quantum algorithm for the kind of problem that we have to investigate? Yeah. So that is basically what I'm trying to bring as a main message. Yeah. Now, why is it important that we have, let's say, something like a quantum library? Yeah. So the full stack. Yeah, I already showed the quantum applications, and then there's quantum library, because we still have to develop maybe new gates, new runs, new parts of the algorithms that other people can also use. Yeah, that's what we see in the genetics part. Yeah. So that's why we need to share maybe at some point. That's why Qiskit is very interesting. We have to. You should look at Qiskit. It has also a public domain quantum library. Yeah. So but this is also where we can define maybe new quantum gates. Yeah. We can experiment in going to larger number of qubits. Yeah. Why shouldn't we try to go to 120? That's 2 or let's say 10 to power 120. These are ridiculous memories that we need, and that's why we need supercomputers. Yeah, but trust me, there are more supercomputers in the world than we're actually using in a useful way. Yeah, and so we have also our language, and that I think is better than the IBM language. We are combining classical logical structures, the if then else, the while loops, and the for loops. Yeah, with the quantum gates. Yeah, and so that is how we really want to make the tight connection between classical computer, classical processor, controlling a lot of these quantum operations, yeah, and the pure quantum operations. Yeah, so that I think is important. We developed our own compiler, and to show where the physics people are. Yeah, this is where I was also for the, let's say, first 5-6 years. I was there, bottom right. Yeah, but you see. Yeah, so that this is the real qubits, yeah, with 10 to the minus 2, 10 to the minus 3 error rates. Terrible. As a computer engineer, I said, hey, guys, really, solve it. Yeah, they're not doing that right now. Yeah, they don't know how to solve it. But okay, that's fine. Yeah, so they have to move up. Yeah, they have to move towards the logical, which is what Preskel said. Yeah, and now we are going to be with QB, and I do hope more and more universities and researchers, we're in the top left. Yeah, so with perfect qubits, and we do it in a virtual way. Virtual way means, yeah, you may have heard that maybe at some point, if 2 qubits need to have a 2-qubit operation, they need to be nearest neighbor. They need to be close to each other. Yeah, in the virtual world, they can be pretty far apart, and we can still do with the perfect qubit, we can still do a perfect operation. Yeah, so that is what we understand by virtual perfect qubits. Yeah, they're far apart, but they can still do a correct quantum gate. And of course, we will have to relax that. We will also have to go to, let's say, logical qubits, and then this may be the part where maybe in 10 years, 15 years, we merge again with the physics world. Yeah, and that we can offer real solutions, quantum solutions to anybody in the world. Yeah, so I think this is what the main part that I wanted to explain here. Yeah, you see this dotted line, because this is the C-quasm. Yeah, and it's only here that we go to the executable quantum. Yeah, so this is a theoretical concept. Yeah, that's why a compiler does certain things, but never translates it into real physical signals. Yeah, but that is something that we did already for Intel, and that we may do for anybody who might be interested, photonics, whatever it is. Yeah, so that is the goal. Now, if you want to go to a classical computer, yeah, remember in the quantum physical world, yeah, actually I think he's Indian, Vazirani, yeah, he's a professor in Berkeley, yeah, California, Berkeley, and he gives a brilliant lesson on quantum information and technology. If you go to edX, yeah, I think there's even a lesson of this year you can follow. It's for free, yeah, incredibly good, yeah. But so, and he tells what is really possible in the quantum physical world and what is not possible, yeah. So in the quantum physics world, there is this implicit parallelism. I call it implicit because there is not a single physics person that will write the quantum circuit in a parallel way. No, this is well done by these electrons or photons or whatever it is. That's where the parallelization is generated in a way that nobody understands. And when I say nobody, it's nobody. Vazirani will also say that in his lesson. Yeah. So I looked at his lesson multiple times. So you can blame me, yeah, and have joy for him. Yeah? But this is clear. So if we want to run any quantum circuits on a classical machine, what we do need to do in an explicit way is to parallelize the quantum circuit. Yeah, if you go, let's say, to 2 qubits, you have 4 states. So that basically means you can have an execution for this part of this part, for this part, or for this part. So that means you have 4 paths. If you go to 10, you have 1024 states. 2 to the power 300, this is a huge number. So you see, it immediately explodes in the number of computations that you need to do. That's why maybe we can go to 50, 60, maybe 100, yeah, depending on how good the classical computer is that we can use to run it. So this is just a way to visualize the parallelization of a quantum circuit. So anybody who is doing computer science and is interested in parallelization, this is a huge topic to look at. Very interesting. Yeah, maybe classical algorithms can be used for that. Yeah, I haven't seen solutions yet. Yeah, and I cannot do everything. So that is why. Yeah, it's no, okay. It's moving. Do you see it moving? No, it's yeah. Okay, well, I go to the next one. I don't know now why that is. Oops. Okay, sorry, we have to go back. There's an interruption in my screen suddenly. It will come back. Yeah, you should see it again.
Okay.
Oh,
Evolution of the number of qubits during execution, right? What you're showing now?
Yeah. Yeah, okay, that's what you see. So you see in this slide, yeah, that we have here, wait, then we're, yeah, oops, wait, where's my mouse? Wait, I have to again put it into red. Yes, I'll do that. Yeah, you see here that you can have multiple. It starts with 1 and then it grows and then it shrinks again. And then that information is transmitted to the next step in the quantum circuit. Yeah, so that is basically what we need to do in any kind of quantum circuit that we want to run on a classical machine. Yeah, so this is how you can show that and there's no understanding, yeah, of these things. Yeah, this is the number of qubits. And on this axis, it's a time. Yeah, so these are time steps. Yeah, where we increase or decrease the number of qubits. So these red lines are the number of qubits that we need in this particular step of the quantum circuit. You see, it's really evolving. Yeah, and so that is what we still need to understand, and that is what you see also here. Yeah, you see here the number here is much bigger than in the beginning and at the end. Yeah, and this is always the same graph, but maybe we still have to understand that. We don't know how to understand. Computer scientists have a look at that. That's a very interesting topic. Yeah. So this is how the number of qubits might evolve. Yeah, in any kind of application. Yeah. And again, it's important. Now I repeat something I already showed in the beginning. we need to do twice 2 to the power n, and n is the number of qubits that we're combining, perfect qubits, yeah? Yeah, that's the kind of amplitude that we need, so at the peta and zeta byte level, so 1000 to the power 6 and 1000 and to the power 7, yeah? So this means, yes, we do need a lot of things, but at least we make it available and accessible for anybody in the world who's interested in investigating it, yeah? So that I think is important. The generic micro, so I'm going down the different layers now, a little bit. I do hope that you understand that. So this is the generic, this is what we're currently developing. So you see that we will send instructions to the QB sim, yeah, and this is what the blue part is the quantum accelerator microarchitecture, yeah. The classical processor is here, yeah. It could be an Intel or a Chinese version of that. I don't, in essence, I don't really care. Yeah, and so you do see we have an instruction cache. We need to translate the address of where the qubits are. Yeah, and the qubits are of course stored in QBSIM, but part of the qubits, they will also be stored, let's say, in the microarchitecture here. Yeah, that's important to understand. And then we have different queues because we need to have a timing. Yeah, if we go to the physical world, the timing from this point on becomes deterministic. Yeah. So whatever we do here in the physical world, if it says nanosecond, 80 nanoseconds, it should be 80 nanoseconds, it should not be 17 or 19, it should be 80 nanoseconds, yeah? So in our classical world, we still want to respect that, but classical machines, they don't require these kind of things, yeah? So we have queues, yeah, and maybe one queue is then related to this QBSIM and another to that one and that one and that one, yeah? I can have maybe up to 10 or maybe 100 QBSIMs running and doing the execution in parallel. That is what the main memory, the quantum accelerator is doing. Okay, there's a database. There are a lot of logical things. Yeah, we try to solve. Yeah, and analyze what we're looking at. Yeah, that we store a lot of the things in a database too. Yeah. Then we have QBSIM. I will not go into the details because it still kind of looks a bit like an empty box. Yeah, it is partly described in the big paper. So if you're interested, I will send you the big paper. Yeah, or through you. Yeah, but that is what is being used, that we use in QB. Yeah, and I want actually, this is an open invitation to universities to use also QBSIM. Yeah. Or improvement of QBSIM or a different simulator. Yeah? There are many simulators, but yeah. And then at some point we will be able to make the move to a quantum chip, but it needs to be much better. Yeah. And I always tell now potential customers of QB, I said, you're not gonna put you're gonna not put all of the errors into my space. You solve those errors. Yeah. Because otherwise they say, yeah, okay, we have it, yeah, Bertels, and you solve the problems. I said, no, I'm not going to do that. I solve a lot of other problems, but not the things that you should be fixing. Yeah, just to be very clear. Yeah, that what I explained already with the compiler. Again, this is the network. Yeah, we're currently working with Amazon. Yeah, this is just an example. Could be Google, could be whatever. Yeah, but this is how we want to combine multiple supercomputers through the internet. Yeah. Now I will give you one example. Yeah, what Aritra is working on is on quantum genetics, and I will not go into all of the details. Yeah, but still, the essence of what it basically means in genetics, where there's always kind of genomic sequencing and analysis. Yeah, and I will explain those things. We have our own OpenQL language. Yeah, so as Aritra is evolving his algorithm, yeah, we need to make extensions of the language. Yeah, and now we're working on the microarchitecture. Yeah, and that's in about 1 month or 2 months or 3 months. Yeah, this is a short time that we will start implementing it to make a first accelerator kind of thing. Yeah, and it will run, of course, on QBC. Yeah. So what is this genetics kind of thing? What is important to understand is that we always are thinking about the human genome, yeah, or any organism in the world has a genetic profile, yeah, because whether we believe it or not, I will not go into that direction, but we all originate from the same kind of living organisms, yeah, some bacteria, and out of which different kind of entities evolved. Some became animals, some became something like a human thing. Yeah, so that is why we always share the same kind of genetic sources. But anyway, we have a reference genome only consisting here of 32 units here, yeah, which is what you see here on the top line. And then we have short reads. And again, we reduced the size of the genome, yeah, because the human genome is a couple of billions tall, yeah, or long. So way too big to do that even now today, or even on a supercomputer, yeah. So we get a lot of short reads, yeah, from one American company, Illumina, yeah, for instance, yeah, and then we need to map how this short read fits somewhere on the reference genome. So here you see now how this particular short read, that it fits here on this particular location, yeah, and you see that it basically fits quite well with all of the colors, yeah, but not with one, yeah. So there is so that's why there is still one error that we find here, but that it's okay, yeah, yeah, and that we have to do with millions or billions of short reads. And this is a very compute intensive work, yeah, which actually years ago, about 10 years ago, I started another company called Bluebee. That's why my youngest daughter, she says, we'll call it now QB. Yeah, that's where the name comes from, but it was Bluebee, who did all of the software. I wanted to have an FPGA acceleration, but then nobody was interested in FPGAs. Yeah, but we did efficient software implementations for the genomic sequencing. Yeah, and now I'm doing the same thing in the quantum world. Yeah, so that is basically what the algorithm is. Yeah, I will not explain those things right now, but simply give again the big picture. So again, we have a very short reference genome here of length 4, and an even shorter short read, yeah, of length 2. So what is then needed? This is what we want to achieve. We need to know where this short read fits into this reference genome, yeah, and then you see that it's red is 0, yeah, and green is 1. Yeah, red is 0 and green is 1. So this is indeed where these things map together with the reference genome. Yeah, in this particular sequence, the sequence is also very important. Eh? So the entire algorithm, yeah, I will not explain it into too much detail. Yeah, but you do see here there is a dotted line that you may see here, and this is from this place on. Yeah, it goes into a quantum reasoning. Yeah. We introduce qubits, yeah, and we introduce operations with these qubits, yeah. So we simply have an index database, yeah, of three components here, but actually it should be 4. It should be 4, yeah, like we see here. That means this is then the superposition. This is in a combination of combining all of those qubits together with each other. Yeah, and then we can start mapping this particular short read, and I can have hundreds or thousands or millions of them. Yeah, to map them onto the superposed kind of qubit states. Yeah, in memory or wherever it might be stored. And then you see here again, we call it the Hamming distance. Yeah, I already showed it in the previous slide, the Hamming distance, which is how well this short read maps on the reference genome. Yes, that's what it is. So then we see the mapping, yeah, and then when it's green, that means perfect match. When it's something is grayish, that means there is no match there. So there is only one good match, which is this one, yeah, and the others only have partial or complete misses. Yeah, that is basically what we do. And of course, we do that on much bigger entities, yeah, so that we have good assessment of the algorithm. So that basically means, okay, this is what we think is a good match for the short read on the reference genome, which is on this particular location, yeah, and which is then the result of what you store into your database, yeah. It's on the 0,0 location of this particular short read that you see here, yeah, on the reference genome. So this is how it matches, yeah, these two parts of the reference genome with the short read, yeah. But this is just an example. So again, there's something like the Hamming distance. Yeah, how big is the difference between the two? Yeah, and again, we see here the Hamming distance between the 0 and the 0, 1. Yeah, so this is the DNA slice. Yeah, so this is the 0, 1, or the this is basically what the DNA slice gives us. Yeah, and this is then the read that we see, yeah, on the reference genome. So we have to match it. We have to see now where this 0, 1, yeah, well, this one where it matches on the with the reference genome. So I have 0, 0 with 0, 1. Yeah, that is what you see here in this Hamming computation, which is a quantum operator that we defined, that Aritra defined, yeah, and which is now being used throughout many of the quantum genetics algorithms, and even in other ones that we're using. Yeah, so you do see here we have the 1, 1, yeah, and that is going. Wait, I have to see now. No, it's a 0, 0 with the 0, 1. The 0, 0. Wait, the 0, 0 with the 0, 1, 0, 1, 0, 1. Yeah, so that is what we see here. Yeah, and we do see that this is the 1, 1, which is the reference genome here. Oh, which is this part. Yeah, and then we have the Hamming distance between the 0, 0 and the 0, 1, and the 0, 1 is the one that we have here as the short read, and that's being mapped onto this one. Yeah, so that's why we have in the final state it's 1, 1, 0, 1, yeah, which is this 1, 1, and 0, 1, which is the Hamming distance. Yeah, so this is becoming the new qubit superposition state, and I can do that also for the other base states. So this is the 1, 1 base state. Yeah, so this was the 0, 1. This is the 1, 1 base state. Yeah, and then we map it between so 1, 0 is this one in the reference genome, and this is then the short read that we get. Yeah, so that's what we see here. Yeah, and again that gives us 1, 1 because there are errors. Yeah, that's why the yellow, yeah, or the purple, yeah, they're both purple, and here is 1 yellow and 1 purple. Yeah, so here we have a worst match. Yeah, and then we still need to do for this one, so it's in the 0, 1 state. Yeah, so it's the 1, 1, and the 0, 1 with the 0, 1 is this one. Yeah, and then is the one right then. I have to see now here 0, 1. Yeah, so this is the mapping, the Hamming distance between those two parts. Yeah, and we're in the 0, 1 state, which is indicated by this one. Yeah, and then we still need to do the final one, the 0, 0, yeah, because this is a perfect match of the reference genome and the short read. So the 0, 1 with this 0, 1, yeah, and this 1, 1 is this, sorry, is this 1, 1, is this 1, 1 with the 0, 1 of the short read, yeah, and this is the 1, 0 in the reference genome, yeah, and the 0, 1 in the short read. So this is how to interpret it, okay? So that each time gives us a complete new superposition kind of state of the qubits that we have. Yeah, and that basically also means they all have the same kind of amplitude, yeah, to be in the correct state. Yeah, because we're just starting the information here. Yeah, and then we do need to apply quantum gates. Again, the logic dictates us that this is the quantum gate. This looks like the simplest kind of thing, yeah, but then we have to change. We have different versions of these things, so theoretically that seems to be correct, and we have to translate these gates, yeah, so everything which is prior to this thing, yeah, oops, yeah, this one, yeah, we have to translate that into the original, into the available qubit states that we have in the state of quantum computing. Yeah, and then of course we have to do the same thing for the last part. Yeah, and that is the translation into the universal gates that we currently can implement on our QB sim, for instance. Yeah, so that is why quantum algorithm development also pushes the quantum gates. Yeah, because maybe it may be interesting to simply have the physical implementation. yeah, and have that immediately as an operation if it turns out to be very useful in other algorithms. Yeah, so that is basically what we're doing, and these are then the mappings, yeah, the amplitudes that we have as we wrote them down here. Yeah, the 0.5. We have those 4 0.5s again for each of the amplitude states. Yeah, so this. Yeah, then these amplitudes that we generate in a C-quantum kind of version. Yeah, so again, these are the amplitudes. This is the figure for the amplitudes. Yeah, you see some of these amplitudes are negative. Yeah, so negative amplitudes. So this is basically the 0. Yeah, so from there it's positive. Yeah, positive, and here it is negative. Yeah, so that's why these are in yellow. And then after a number of iterations of let's say the quantum algorithm, yeah, it destabilizes these amplitudes. They don't change anymore, and that means you've reached the end of your algorithm. And then you have to translate that into probabilities. Yeah, so that is what you see here, and the probability is basically the same thing as the alpha, yeah, and the beta. Yeah, you take the absolute value of each of them. Yeah, I'm drawing it here now, and you square them. Yeah, square them. Yeah, and then you add them together, because the amplitudes, if you turn them into probabilities, you always get 1. Yeah, the probability that your solution is somewhere in this graph is always 1. Yeah, if you add all of the probabilities together, and that's why you see now all of these probabilities. Yeah, they're plus again. Yeah, so the negative signs have disappeared. That's what the absolute value and squared. That's what it means. The amplitude is turned into a probability. Yeah, and then the one with the highest probability is the one which will be measured most of the time. So this basically contains a solution of the mapping of your short read onto the reference genome. Yeah, this is how it this is basically how it goes. And this needs to be every quantum algorithm. Yeah, you need to run it multiple times. Yeah, such that you will get, maybe at some point, I will draw that maybe here. Yeah, you need to draw it, and you need to have some time. Yeah, you need to count each time which qubit state. Yeah, so this is q whatever it is. Q, it looks like a 0. It should be a q. Yeah, q1. Yeah, and you can go to any kind of quantum gate. Yeah, that you can compute, and the one with the highest probability is then the most likely good candidate for your algorithm. So that's why we need multiple runs of the same algorithm on the same number of qubits with the same parameters. But because of the probability in the quantum algorithm, yeah, you may go left or you may go right. Yeah, in the quantum physical world, but also in the classical execution. Yeah, that is why in the end, all of the quantum states, all of these possibilities are stored somewhere already in memory. And we still need to see, okay, oh, this is the same value as this one, and this one is the same value as the other one. And you keep on you keep on counting the number of times that this particular solution was computed and found. Yeah, and you will see here, maybe we'll have 2 or 3. Yeah, and here we have many more. So this is why this particular solution is the correct solution for your quantum algorithm. Yeah, so this is important to understand of how it actually works, how this algorithm works. And this is done by Aritra, simply for his PhD in quantum genetics. Yeah, and he invents all these kind of new gates. Yeah, which is very good. Yeah, and this is how we can expand and make the quantum language evolve, or quantum applications evolve in an efficient way. Yeah, in the end, so this is something that we still have to do. Yeah, we have to make a quantum genetics accelerator. Yeah, you see here we have DNA. Yeah, we have genome sequencing instruction, but this is basically the same thing. Yeah, this is the same thing. We have a DNA database. Yeah, because we need to have multiple runs, such that in the end we do know what the correct mapping is of all of the short reads onto the reference genome. Yeah, that is why we do need a database to store all that information. Yeah, that is basically what the entire work in genomics is doing these days. Yeah, I can start concluding, and we only have like 3 slides left. Yeah, so this is a new figure that we put also in our big paper. Yeah, so if you're interested, please send me an email. Yeah, or ask Vishnas. But it's important that we move into a different direction. This is where everybody in the quantum physics world and actually in other worlds, yeah, other fields are looking at. They're looking at real qubits and realistic qubits. These are improved qubits, 10 to the minus 4, 10 to the minus 5. I have not seen a single paper about that. Yeah, just to know that this is like, okay, wait for it for 10 years, 20 years, but you're wasting time. Well, or the world is wasting time because even the application, it takes time to develop. So that's why, yeah, assume perfect qubits. Yeah, and even Qiskit is allowing that. And then you can work on any kind of application, quantum, to build a quantum accelerator. We can do that. Yeah, that is very important. Yeah, such that we can avoid the same graph as I showed before, the hype cycle, that everybody's super enthusiastic. And then here says like, okay, but where is the solution now? Yeah, and that will happen. It will happen. This happened with everything which is already going downwards here. Yeah, yeah. You see here blockchain, virtual currencies. One company still working on virtual currencies is IBM. Has made a full infrastructure to have blockchain, yeah, or a virtual currency available in the world, in the market. But if the law is not there, if the economies, so companies are not doing it, then why would you put money and put it on the market? Yeah, and the same may come for quantum. Yeah, and I do hope it will not be as bad. Yeah, but I do think that we should target maybe something 10, 15 years away, but start educating people right now so that they can do their master thesis and probably maybe also a PhD thesis. Yeah, and go to a good university that it has some background in that. Yeah, I'm not working in Delft anymore, but Delft starts having a good background. Bit too much physics oriented. Yeah, maybe University of Leuven will be a bit better. I don't know. Yeah, but I'm not changing anything right now there. But this is currently my vision. Yeah, that we need to look at. Yeah, and so in conclusion, yeah, I showed what that actually means to make a full stack quantum accelerator. What are the layers from higher level application, the library, the language, yeah, testing software, operating system software, maybe, yeah, to a microarchitecture, to the mapping and the routing, yeah, to if you do need the routing, the qubits to be close to each other, then of course it is important that you're capable of doing that, yeah, and then QBSIM to run it, yeah, that is basically what it means, yeah, that's what I describe here. We clearly need more international collaboration. So I'm in the team that I had in Delft. There was basically not a single Belgian, yeah, but we had the people from all over the world, China, India, all over Europe, yeah, Latin America even, yeah, but I want to keep on promoting international collaboration. So I do have some positions open, but I think they're basically filled. Yeah, but keep an eye on what's happening in Europe. Maybe there will be many opportunities, yeah, for a PhD there. Yeah, we run it on classical machines, and of course, at some point we cannot avoid it, and I do hope that will happen. Yeah, better sooner than later. That there will be a good quantum chip. Yeah, but that means 10 to the minus 6, 10 to the minus 7, not minus 2 and minus 3. Forget it. You cannot do anything meaningful with that. But minus 6, minus 7. Remember, minus 15, minus 16 in CMOS. Yeah. So what the classical machines are. So I'm not so optimistic that we will reach that. But minus 7, minus 8. Why shouldn't we try to go for that level? Yeah. But we are not there at all. Voilà. That's basically my storyline. Thank you.
Thank you so much, sir, for this amazing session on quantum computing. I wanted to be asking questions, but most of the questions were being answered through the slides. And it actually reduced my work to an extent that I needed have to have too much editing or else too much overlays on the video. And it was amazing having this podcast with you as a form of a session. It was an eye-opener for me because we have been studying a lot on quantum computing. We have been studying a lot on different technologies that can get involved. But I think when I saw the TED talk, sorry for not mentioning it in the message, Like I wanted to see the TED talk, but like after seeing the TED talk, there was a new dimension for my thinking process over the quantum computing. I think this clarified everything. Thank you so much, sir.
Okay, okay. All right, thank you very much for the invitation. And I do hope that that people are interested in reading the big paper. So I think I already sent it to you. So, but otherwise I made maybe small changes to it. Maybe I will send the current version and it will evolve. Yeah, but this is this, and it's an open thing. So I want to share a lot of things, yeah, such that people can do whatever they feel is necessary. Yeah, and as a company we will also do that. Yeah, and maybe we will be in India too at some point, but anyway, we start in Europe. Yeah, but also with the Malaysian Singapore investor. Yeah, that is very clear, and then we'll see where we end up and how fast we can make it into a real product in the market. Okay.
Yes, sir.
All right.
Sure. Thank you so much. Thank you so much for giving the session. Yes,
Okay.
I stopped the
Thank you.
recording.